Module 7, Lecture B, Super and Methods. By the end of this lecture, you will be able to use Super to call parent-class implementations correctly in single and multiple inheritance scenarios. Define and use class method and static method to represent behaviors tied to classes rather than instances. And create and use memory view objects to share slices of binary data without copying. Mastering super calls. Basic super usage. When reusing behavior from a parent class, think in terms of specialization rather than replacement. A child class usually wants to keep what the parent already does and simply add extra steps before or after that behavior. For example, an international order can use the parent's price calculation and then add customs fees on top. By delegating to the parent's method and then extending it, the child class avoids duplicating code and stays loosely coupled to the parent's implementation. In single inheritance, delegation means explicitly asking the parent class to run one of its methods while still operating on the same object. This keeps the link between the class and its instance, so the method can use the object's attributes through the self parameter. For example, a custom button in a graphical interface can first call the parent button's click behavior to handle the usual visual updates, then add its own logging. This allows the child class to extend the parent's behavior without needing to know how the parent is implemented internally. Using a delegation mechanism instead of directly naming the parent class makes code more robust and easier to maintain. Hard-coding the parent's name creates fragile dependencies that can break when the inheritance structure changes, such as when a new base class is added. Delegation automatically refers to the next class in the chain, so the code adapts to these changes without manual updates. This is especially valuable in large systems, like financial applications, where class hierarchies evolve over time, and it helps ensure each specialized class reliably extends its parent's behavior and reduces bugs. Python code. Basic super usage. In this section, we will demonstrate basic use of the super mechanism with simple order classes, focusing on how it helps structure object-oriented code. You will see how child classes can extend and refine the behavior of their parent classes in a clean and maintainable way. We will also compare making direct calls to parent methods with using super-based delegation, highlighting how super provides a more flexible and scalable approach to reusing and customizing parent behavior. We define a class called order to represent a basic order that has a price. Inside this class, the initialization method sets up each new order object. This method takes a reference to the current object and a base price in dollars. It then stores that base price in an instance variable, so the order's price can be accessed and used throughout the class. This function computes the total price for an order by first printing a message that indicates the calculation is running for a base order, which helps track which class's method is being used in a class hierarchy. It then returns the base price stored in the object expressed in dollars. This returned value represents the total cost of a simple order without any extra fees or modifications. In this example, the class called International Order Bad extends the order class and defines its own total price method. When this method runs, it announces that it is calculating the total, then explicitly calls the total price method from the parent order class by using the class name and passing in the current object. It takes that base total, adds an extra fee of 15, and returns the final amount. This works. But directly referencing the parent class like this can be less flexible in more complex inheritance situations. In this example, we create a class called International Order Good that inherits from the order class and overrides the total price method. When this method runs, it announces that the calculation is starting, then calls the parent class's total price method using the super function. This ensures that any future changes to the parent method are automatically included, keeping the code flexible and easier to maintain. After getting the base total from the parent, it adds 15 units as an extra fee for international orders and returns this new total. We begin by creating a simple order with a base price of $20, which initializes an instance of the order class. We then call the method that calculates the total price and print the result. At this stage, the total price method just returns the base price, so the total is $20. This basic example shows the core behavior of the order class before adding any extra features or complexity. We create a new international order using a less flexible design by making an instance with a base price of $20. When we call its total price method, it announces that it is running and then directly uses the parent order class's total price calculation. It adds a fixed fee of $15 to the base price. The final result is a printed total cost that combines the original price with this additional international fee. We create a new international order using the improved version of the class, giving it a base price of $20. We then call its total price method, which uses the parent class's total price calculation so that any future changes in the parent are automatically applied. The international version adds an extra $15 to cover international fees. Finally, we print this combined total as the final cost of the international order. This script illustrates inheritance in Python and why using the super function is preferred. It defines a base order class with a method that returns the base price, then two international order subclasses that add a fixed fee. One subclass calls the parent method directly, while the other uses the super function, which is more flexible and recommended. When run, all versions produce the expected total prices, but the example emphasizes that using super leads to cleaner and more maintainable code. Understanding method resolution. To understand how the super keyword works in Python, you first need to know about method resolution, which is how Python decides which method to run in an inheritance hierarchy. Each class has a method resolution order, or MRO, which is the sequence of classes Python searches when you access an attribute or call a method. When you use super, Python does not simply go to the immediate parent class. Instead, it moves to the next class in this MRO and looks for the method there. Because of this, super is tightly linked to the MRO, and knowing that order is essential for predicting which method will actually be executed, especially in complex inheritance structures. In simple single inheritance, Python looks for methods, starting with the instances class, then its parent. and continues up to the base object class. When you call the super function, you tell Python to start searching just after the current class in this chain. For example, if a specialized bank account inherits from a general account, which inherits from a financial entity, using super in the specialized account moves control to the general account. This lets each class extend or modify behavior from the one before it, without hard-coding parent class names, making the design more flexible and easier to maintain. In multiple inheritance, a class can combine features from several parent classes, such as a user interface component and a logging component. Python handles this by creating a single, linear order for looking up methods that respects both the order of the base classes and their internal hierarchies. When you call the super function, Python follows this order to decide which class should handle the call next, so each class can cooperate without repeating or skipping work. To keep this flow of control smooth, especially in complex systems like graphical interfaces or frameworks with authentication or caching, it is important to use the super function consistently throughout the hierarchy. Python code. Understanding method resolution. This lesson demonstrates method resolution order using simple classes with single inheritance. It shows how the super function automatically follows the method resolution order chain when calling methods in parent classes. To make this behavior clear, the program prints each class name and the full method resolution order list, so you can hear exactly how Python decides which method to run. We define a class called vehicle that contains a method named describe. When this describe method is called, it prints a message indicating that the method in the vehicle class has run. This creates a basic behavior that can be inherited by other classes. Subclasses can then extend or override this method, which helps demonstrate how method resolution works in an inheritance hierarchy. Here, a class called car is defined as a child of a class called vehicle. Inside car, there is a describe method that first announces that the car version of describe is running. It then uses the super function to call the describe method defined in vehicle. This lets car add to or change the behavior of the original vehicle describe method while still reusing its functionality. This part of the code defines a class called sports car that inherits from a class named car. Inside sports car, there is a describe method that first announces that the sports car version is running. It then uses the super function to call the describe method from the car class, which is its direct parent. This shows how a subclass can extend or modify behavior while still reusing functionality from its superclass through method resolution order. We create an object from the sports car class, which inherits behavior from the car and vehicle classes. We then call its describe method, which first runs the version defined in sports car. Inside that method, the super function is used to call the describe method from car, which in turn calls the describe method from vehicle. This sequence of calls shows how method resolution order works, as each class in the inheritance chain has its describe method executed in turn. We begin by printing a message to show that we are about to display the method resolution order for the sports car class, which reveals how Python decides which method to use when multiple classes are involved. Then we go through the method resolution order list that Python automatically creates for this class. For each class in that list, we print its name. This lets us clearly see the inheritance chain and understand how method calls are resolved, especially when using the super function. This script uses a simple inheritance chain of vehicle, car, and sports car to demonstrate how Python's method resolution order works. Each class defines a describe method, and when describe is called on a sports car object, it first runs the sports car version, then the car version, and finally the vehicle version by using the super function. The script then prints the method resolution order for sports car, showing the exact sequence of classes Python checks when looking for methods. This gives a clear, practical view of how Python resolves method calls in an inheritance hierarchy. Cooperative multiple inheritance. When moving from single inheritance to designs with multiple parent classes, using the super mechanism correctly is essential for predictable behavior. Cooperative multiple inheritance means each class follows a shared convention so that all relevant methods are called in a proper sequence. For example, in a document workflow with stages such as validation and logging, each stage can be a mixin that uses super. This allows one method call to trigger every stage in order, without any class needing to know the full inheritance structure. This is a big problem rather than a single parent class. Without any class needing to know the full inheritance structure. In cooperative multiple inheritance, classes rely on the method resolution order, or MRO, instead of calling specific parent classes directly. By using the super function, each class hands control to the next method in the MRO, so the runtime decides which method runs next. This means you can change the class hierarchy, such as adding or reordering mixin classes for authentication, compression, or encryption in a network client, without changing the method calls themselves. As long as each mixin uses super correctly, the MRO ensures that all behaviors are executed in a consistent and correct order. Cooperative multiple inheritance helps avoid bugs that occur when some classes ignore the shared calling protocol and directly invoke a specific parent. Skipping the shared method chain can bypass important behavior, such as required initialization or checks, and lead to inconsistent or unsafe states. By always using the shared method call, you ensure that all necessary behaviors run in the correct order. This supports modular design and makes components easier to test, reuse, and combine into complex behaviors without needing to understand the entire class hierarchy. Python code cooperative multiple inheritance. Demonstrate how cooperative multiple inheritance works by using the super mechanism across mixin classes so that each mixin can contribute its behavior without needing to know the full class hierarchy. Show that with this cooperative approach, every mixin calls the next appropriate method in the chain, allowing all classes to participate cleanly. Then contrast this with non-cooperative designs where classes call their direct parent methods explicitly, which can break the method resolution order and prevent some mixins from being invoked. The base request class defines a send method that prints a message saying it is sending a raw message, then returns the message it received. This provides a simple, default way to send messages. The class is intended as a basic foundation that other classes can extend or modify to create more specialized message sending behavior. The auth-mixin class is designed to add authentication behavior to a message-sending process. Its send method first announces that it is adding an authentication header, then modifies the message by adding an auth tag and a separator in front of the original content. After updating the message, it calls the send method of the next class in the hierarchy using the super mechanism. This lets the auth-mixin work cooperatively with other mixins in the class hierarchy while contributing its own authentication step. In the compress-mixin class, the send method takes a message and first prints a note that it is simulating a compression step, indicating where real compression logic would go. It then modifies the message by wrapping it with the word compressed to represent the effect of compression. After this modification, the method calls the send method of the next class in the inheritance chain using the super mechanism. This allows other mixin or base classes to continue processing the message in a cooperative way. The bad encrypt mixin class defines a send method that announces it is encrypting data, then alters the message by wrapping it with the word encrypted in brackets. However, instead of using cooperative inheritance through the super function, it directly calls the send method of the base request class. By bypassing the normal method resolution order, it breaks the cooperative chain of method calls. This can disrupt the intended behavior when multiple inheritance is used, because other classes in the hierarchy may never have their send methods invoked. In the GoodEncrypt mixin class, there is a send method that takes a message and first announces that it is encrypting the message and will use cooperative super behavior. It then simulates encryption by wrapping the message with the word encrypted in square brackets. After modifying the message, it calls the send method of the next class in the method resolution order using the super function. This design allows the mixin to add encryption behavior while still cooperating cleanly with other classes in the inheritance chain. Bad client is a class that inherits from several mixins and a base request class to combine multiple behaviors into one client. It first uses bad encrypt mixin for encryption, then auth mixin to add an authentication header, followed by compress mixin to simulate compression, and finally base request to send the raw message. This order is meant to layer encryption, authentication, compression, and sending. However, because bad encrypt mixin does not use cooperative inheritance, it breaks the normal method resolution order and can cause the message processing steps to run in an unexpected sequence. The good client class inherits from several mixin classes and a base request class, allowing it to use cooperative multiple inheritance. Each mixin adds its own behavior to the send method while calling the next implementation in the method resolution order through the super function. This means every mixin can contribute functionality without needing to know the full class hierarchy. Good client itself defines no new methods or properties. It simply combines the behaviors of its parent classes to demonstrate an effective structure for cooperative inheritance. We begin by printing the method resolution order for the bad client class to see the sequence Python uses to search for methods and understand its inheritance structure. Then we announce that we are about to send a message using bad client, which includes a non-cooperative mixin. We call the send method on a bad client instance with the message hello from client, which activates the chain of methods defined by the class hierarchy. Because of the non-cooperative mixin, some of the expected cooperative behavior is skipped. Finally, we print the result of the send operation to show the final processed message after all relevant methods have run. We begin by printing the method resolution order for the GoodClient class to see the exact sequence Python uses to look up methods, which illustrates how the mixins cooperate. Then we announce that we are about to send a message using this GoodClient class that relies on cooperative mixins. We call the send method on a GoodClient instance with the message hello from client, which triggers a chain of method calls across the mixins. Each mixin modifies the message in turn. And finally, we print the fully processed message, showing the final result produced by the cooperative inheritance chain. This material explains cooperative multiple inheritance in Python, using mixin classes that each modify a message. A base request class sends a raw message, while mixins add authentication, simulate compression, and apply encryption. One encryption mixin breaks the cooperative chain by calling the base request directly. So the authentication and compression steps are skipped. Another encryption mixin uses cooperative supercalls, allowing all mixins to run in order. Comparing the outputs of the two client classes shows that only the cooperative version produces a final message that includes encryption, authentication, and compression, illustrating why cooperative inheritance is important. Class and static methods. Class method factory patterns. Class methods are especially useful as factory patterns, providing expressive ways to create objects without calling the constructor directly. They can bundle specific construction steps, such as building an object from configuration data or database records. Because a class method receives the class itself as its first argument, it works correctly with inheritance, so subclasses create instances of themselves. This separates the intention of creating an object from the low-level initialization details, making object construction more flexible and easier to manage. Consider an online customer account system where the main constructor needs core fields like an ID, name, and status. But accounts can originate from different sources, such as legacy data, web forms, or cache entries. Each of these creation paths can have its own class method that interprets its specific input and then calls the main constructor. For example, one method might parse a log line, while another uses configuration data to create an administrator account. Giving these methods clear, purpose-based names, such as from legacy record or from environment, makes the code easier to read and avoids repeating parsing and validation logic throughout the system. Class methods used as factory methods are especially helpful when working with subclasses because they preserve polymorphic behavior during object creation. If different customer types each need their own setup, factory methods on the base class can still return the correct subclass automatically. This centralizes and simplifies the creation logic, while allowing subclasses to adjust or extend it as needed. As a result, it becomes easier to evolve larger systems without forcing callers to know the details of how each specific type is instantiated. Python code, class method, factory patterns. This section explains how to use class method factory patterns to create account objects more easily. It shows that different factory methods can all build new accounts using the same underlying constructor, which keeps object creation consistent and centralized. It also highlights that when subclasses inherit these class method factories, they automatically gain the same convenient creation tools without extra code. Overall, the focus is on simplifying and unifying how account instances are created across a class hierarchy. The account class starts with a constructor method that creates and sets up new account objects. It takes 3 inputs: an identifier, a name, and a status. These values are stored as the object's own data, where the identifier is usually a unique number. The name is the account holder's name, and the status shows if the account is active or inactive. This design lets each account object manage its own information, so multiple accounts with different details can be created and used easily. This description explains a class method that builds a new account object from a legacy text record. It cleans the input string, splits it by commas, and interprets the first part as an identifier, using 0 if it is missing or cannot be converted to an integer. The second part is taken as the name, or set to unknown if it is not present. The third part is treated as the status, or set to inactive if it is missing. Using these 3 values, the method then returns a new instance of the account class. This description explains a class method that works on the class itself rather than on a specific object. The method creates a new account using fixed default values. It assigns an identifier of 999, uses the name admin user to indicate administrative privileges, and sets the status to active to show the account is currently in use. It then returns a new account instance with these predefined settings. The describe method belongs to the account class and returns a short text summary of an account. It builds a sentence that includes the account's identifier, name, and status. This provides a clear, human-readable description of a specific account instance. It helps users quickly understand the current state of the account at a glance. We define a new class called Premium Account that inherits from the existing account class, so it automatically gains all of account's properties and methods. In the initializer for Premium Account, we first call the parent class initializer using the super function to correctly set up the identifier, name, and status, just as in a regular account. After that, we add a new attribute named Premium Support Hours set to 24, which represents the number of hours of premium support available each day and is specific to Premium Account. In this approach, the method first calls the describe function from the parent class using the super keyword to get the basic account description. It then extends that description by adding information about premium support. The added text explains that premium accounts include support that is available 24 hours a day. This highlights a key feature that distinguishes premium accounts from regular ones. We begin with a text record from a legacy system that holds an account's identifier, name, and status as comma-separated values. The account class provides a special class method called FromLegacyRecord that knows how to interpret this text. It splits the string into its parts and uses them to create and initialize a new account object. The resulting object, stored in a variable, represents an account that has been reconstructed from the legacy data format. We use a class method called FromLegacyRecord to create a new premium account object from a legacy data string. This method splits the string to pull out the identifier, name, and status, then uses those values to initialize the premium account. By using this class method, premium account follows the same factory pattern as the base account class, so all account types are created in a consistent way. In this example, we use a class method called FromEnvironment on the account class to quickly create a predefined administrative account. The method automatically sets the account's identifier to 999, the name to admin user, and the status to active. This lets us instantiate a standard admin account without manually entering each attribute. It illustrates how class methods can simplify creating consistent, standardized objects. We begin by printing a message to show that we are about to describe a regular account. We then use a type checking function to confirm the class of the account object we created earlier. After that, we call the account's describe method, which returns a string with key details such as its identifier, name, and status. Finally, we print both the type information and the description together to clearly summarize the account's characteristics. We begin by printing a message to indicate that we are about to describe a premium account, which sets the context for the output. Then, we use the type function to display the class of the premium account object, confirming that it is an instance of the premium account class. Finally, we call the describe method on this object, which returns a string that combines the basic account information with its premium features, such as premium support hours, giving a complete description of the account. We begin by printing a short message to signal that we are about to describe the admin account, which sets the context for the output. Then we use the type function to display the class of the admin account object, confirming that it is an instance of the correct class. Finally, we call the describe method on this object to produce and print a clear, human-readable summary of the account's attributes, making the output easier to understand. This script illustrates how class method factory patterns can simplify creating account objects. It defines an account class with one factory method that builds an account from a legacy record string and another that builds an account using predefined environment values. A premium account subclass inherits these factory methods, so it can create premium accounts with extra features using the same patterns. When the code runs, it creates a regular account from a legacy record, a premium account from a legacy record, and an admin account from environment settings, then prints each account's type and description to show how the shared factory methods streamline object creation across classes. Static utility methods. Static methods are utility functions that belong to a class, but do not depend on any specific object or shared class data. They conceptually fit with the class, yet they do not need access to its internal state. For example, a bank account class might use a static method to validate an account number or calculate a service fee without using details from a particular account. Organizing such operations as static methods makes related functionality easier to find and keeps these methods simple and easy to test on their own. Use a static method when a behavior belongs conceptually to a class but does not need access to any specific object's data or the class's shared settings. For instance, a dataset class might use static methods to check file extensions or standardize column names, since these actions relate to datasets in general but do not modify a particular dataset. A geometric shapes class might similarly provide static methods to compute distances or convert angles without relying on instance data. Grouping these utilities as static methods keeps them tied to the class's domain while avoiding clutter in the global namespace and making the codebase more organized. Static utility methods are helpful because they do not depend on object or class state, so they can be reused in many parts of a system without causing side effects. This is especially valuable in large applications where many teams share common functionality. For example, a user authentication class might provide static methods for hashing passwords or checking email formats that any part of the code can call. Grouping these stateless utilities inside the relevant class clarifies their purpose and supports a clear, well-structured architecture. Python code. Static utility methods. This example focuses on using static utility methods inside a simple class. Static methods do not depend on any instance data or the internal state of the class, so they behave the same no matter how or where they are called. By grouping related utility functions together inside a single class, you make the code easier to navigate and maintain, while clearly separating logic that does not rely on object state. The Distance Tools class is a utility class that groups together simple distance calculation functions. It includes a brief description of its purpose in a docstring, explaining that it provides tools for basic distance-related operations. The class is organized so that related functions are easy to find and use. It relies on static methods and does not depend on any instance or class-level data to perform its calculations. The constructor method creates a new object of a class by taking a home zip code as its single input. It saves this zip code as an instance variable, so each object can store its own home location. This design lets other methods in the class easily access and use the specific home zip code for that object whenever needed. This static method converts a distance from miles to feet without needing an object of the class. Inside the method, a constant is defined for the number of feet in 1 mile, which is 5280. The method multiplies the given number of miles by this constant and returns the result, providing the equivalent distance in feet. The estimate taxi cost method is a static method, meaning it does not use any data from a specific object or from the class itself. It estimates the price of a taxi ride based only on the distance traveled in miles. The method starts with a fixed base fare of $3, then adds a per mile charge of $2.50 for each mile. It returns the total estimated cost by adding the base fare to the distance in miles multiplied by the per mile rate. We start by defining a variable that stores a trip distance of 2.5 miles. This value will be used to convert the distance into feet and to estimate the taxi fare. Setting this distance lets us demonstrate how the static methods in the Distance Tools class can perform these conversions and cost estimates without creating an object from that class. The program displays the phrase trip distance in miles, followed by the value stored for the trip distance. This output clearly shows how far the trip is in miles. Presenting the label and value together makes the result easy to read. It also sets clear context for any calculations that use this distance later in the program. In this example, we print the trip distance after converting it from miles to feet. To do this, we call a static method named miles to feet from the distance tools class, passing in the trip distance in miles. The method multiplies that value by 5,280, which is the number of feet in 1 mile. The final result is then included in the printout, showing the trip distance measured in feet. This code prints the estimated taxi cost in dollars by calling a static method from the distance tools class, using the trip distance in miles as input. The method computes the fare by adding a base charge of $3 to the miles multiplied by a per mile rate of $2.50. This example shows how a static method can perform the calculation without creating an object of the class, keeping the focus on the cost formula itself. We create an instance of the distance tools class using a sample zip code, such as 10001, which sets a home zip code attribute inside the object. However, this attribute is not actually used by the static methods in the class. The main reason for creating the instance is to show that static methods can still be called through an object, even though they do not depend on any data stored in that specific instance. In this example, a static method called miles to feet is defined in a class named distance tools, and it is being called through an instance of that class. This shows that static methods can be accessed using an instance even though they do not depend on any data stored in that instance. The method simply converts a trip distance measured in miles into feet and prints the result. Overall, it illustrates that static methods in Python are flexible and can be used without needing to create or rely on instance-specific information. The program prints the estimated taxi cost in dollars by calling a static method from the distance tools class through an instance named home distance tools. Even though it is called on an instance, the method is static, so it does not use any data specific to that instance. It takes the trip distance in miles as its input. The method calculates the fare by adding a $3 base charge to the trip distance multiplied by a per mile rate of $2.50, and then prints the result to the console. This script uses a class called distance tools to show how static methods can perform distance-related calculations. One static method converts miles to feet, and another estimates a taxi fare from a distance in miles. When the code runs, it prints the trip distance in miles, then the same distance in feet, and then the estimated taxi cost in dollars. It demonstrates that these static methods can be called directly on the class or through an instance, and both approaches produce the same results. This confirms that static methods do not depend on any specific object or class state. Using class and self. To understand class and static methods, it helps to know the roles of self and class. These names are conventions, not special keywords, but they make code clearer. Self refers to a specific object with its own state, while class refers to the class as a whole, including shared settings and ways to create objects. Keeping this distinction in mind guides whether a method should be an instance, class, or static method, which supports clear responsibilities and easier maintenance. In object-oriented programming, an instance method automatically receives the current object as its first argument, often called self, so it can work with that object's specific data and behavior. This makes instance methods suitable for actions that depend on an individual object's state. In contrast, a class method receives the class itself as its first argument, often called CLS, which is useful for working with information shared by all instances and for creating new instances. By using the class as the first argument, class methods can build objects from external sources like configuration files or databases. And this same construction logic can be reused by subclasses without modification. Static methods are different because they do not automatically receive a reference to an object or the class, so it is important to know when to use self or CLS instead. If a method needs to work with a specific object and its data, it should be an instance method that uses self. If it needs to work with the class as a whole, it should be a class method that uses CLS. When a method only performs a task that does not depend on any particular object or class state, it can be a static method, such as checking whether an email has a valid format. Clear separation between these kinds of methods helps keep your code organized and easier to maintain. Python code, using CLS and self. This content should clearly show the difference between using self and using CLS in methods, and demonstrate how instance methods, class methods, and static methods behave. The goal is to explain that self refers to a specific object instance, while CLS refers to the class itself. It should also highlight how instance methods work with individual objects, class methods work with the class as a whole, and static methods are independent of both. The explanation and examples should stay simple, readable, and friendly for beginners. We define a class called discount_calculator that includes a class-level attribute named base_discount%, initially set to 10. This attribute stores the default discount rate that applies to every object created from this class. Because it is defined at the class level, all instances share the same default value. Changing this class-level discount updates the default rate for all instances at once. In Python classes, the init method is a special function that sets up new objects when they are created. In this example, it receives a customer name and a purchase amount, then stores them as instance variables using the self keyword. This gives each object its own customer name and purchase amount, so the class can keep track of data specific to each individual instance. In the apply_discount method, we first find the discount amount by taking the purchase total, multiplying it by the base discount percentage, and converting that percentage to a decimal. We then subtract this discount amount from the original purchase total. The result is the final amount the customer needs to pay after the discount is applied. The first print statement explains that the method is using instance attributes, highlighting that it relies on the self-reference to access them. The second print statement then shows the customer's name, the original purchase amount, and the final amount after the discount is applied. Together, these statements illustrate how an instance method can access and modify data that belongs to a specific object. This class method, called setBaseDiscount, takes the class itself and a new discount percentage as inputs. It first reports that a class method is being used and shows the current base discount percentage stored in the class. It then updates this class-level discount value to the new percentage and prints the updated value. By changing the class attribute, this method adjusts the discount percentage for all instances of the class at once, illustrating how class methods can modify shared class data. This description explains a static method called dollars to cents that takes an amount in dollars and converts it to cents. It does this by multiplying the dollar amount by 100 and casting the result to an integer, so the value is a whole number, which is useful for precise calculations. Because it is a static method, it does not rely on any instance or class attributes. Finally, it prints a message indicating that it is a static method and shows both the original dollar amount and the calculated value in cents. The setBaseDiscount class method is called on the discount calculator class with a new discount value of 15%. Inside this method, it first prints the current base discount, which is stored as a class-level attribute, and then updates that attribute to the new value. This example shows that class methods can change data shared by all instances of the class, so the updated discount applies everywhere the class is used. We create a discount calculator object using Alice's name and her purchase amount of $120, which initializes the instance with these values. We then call the method that applies the discount, which uses a shared base discount percentage stored at the class level. This method computes the discount, subtracts it from the original purchase amount, and finds the final amount Alice must pay. It then prints the customer's name, the original amount, and the discounted total, showing how an instance method uses the object's stored data to perform its calculation. The dollars to cents method is a static method in the discount calculator class that converts a dollar amount into cents. It does this by taking the dollar value, multiplying it by 100, and then printing the result. Because it is static, the method does not rely on any object data or class attributes, so it works independently of any particular instance of the class. IsScript uses a discount calculator class to show the difference between instance, class, and static methods in Python. A class method changes a shared base discount value for all objects, updating it from 10 to 15%. An instance is then created for a customer named Alice, and an instance method uses the new discount to compute and display her original and discounted purchase amounts. Finally, a static method converts a dollar amount to cents without using any instance or class data, illustrating a method that is logically related to the class but independent of its state. Memory View Essentials. Bytes to Memory View. A memory view lets you access a block of binary data, such as a file or network packet stored as bytes, without making a copy. It acts like a lens over the original data, so you can examine and slice it directly. This avoids unnecessary duplication, which is especially important for performance with large datasets. As a result, Memory View is very useful in time-sensitive operations where efficiency matters. A memory view of a bytes object is like placing a clear overlay on top of the original data, so you can look at different parts without copying anything. You can adjust this view to focus on specific sections or share it across your program, but the underlying bytes stay the same. Because bytes are immutable, the memory view is read-only, which lets you inspect and slice data efficiently without changing it. This makes memory views especially useful for tasks like parsing binary formats or scanning large files, where you want flexible access to data while avoiding unnecessary duplication. The main benefit of using a memory view with bytes is efficient integration with other system components. For example, A server can receive a large binary message, store it in one bytes object, and then create separate memory views for different parts, such as the image data and its metadata. These views can be passed to functions without creating new buffers or copying data. This makes memory views especially useful in scenarios like streaming media or real-time analytics, where both speed and memory efficiency are critical. Python code, bytes to memory view. This section explains how to create a memory view from a bytes object without copying the data. So the memory view directly references the same underlying immutable bytes buffer. It emphasizes that changes cannot be made through the memory view because the original bytes are immutable, but the shared buffer relationship is important for understanding how data is accessed. It also compares slicing a bytes object, which creates a new copy, with slicing a memory view, which creates a new view on the same data and can therefore be more efficient. Overall, the goal is to build intuition about how memory views help avoid unnecessary data copying when working with bytes. Recreate an immutable bytes object to represent a sequence of binary data, here based on a simple string of characters. Because it is stored as bytes, the data cannot be changed after creation, which helps prevent accidental modification and can be more efficient. In this example, the bytes contain a mock header and payload, similar to what you might see in data processing or network communication tasks. A memory view created from a bytes object provides a direct window into the same underlying data without making a copy. This means you can access and work with parts of the data efficiently, avoiding the extra cost of duplicating it. Such an approach is especially helpful with large data sets or performance-critical code because it allows direct interaction with the data buffer while minimizing memory overhead. We take the original bytes object and split it into two parts using slicing. The first slice takes the first 10 bytes, which we treat as the header, and creates a new bytes object containing only that section. The second slice starts at the 10th byte and includes all remaining bytes, forming another new bytes object that represents the payload. These two slices are independent copies, so we can work with the header and payload separately without affecting the original data. We create a header view by slicing the memory view to show only the first 10 bytes, which gives us a window into that part of the original data without copying it. Then we create a payload view by slicing from the 10th byte to the end, again, just referencing the same underlying bytes. This way, we can work with different sections of the data efficiently while keeping memory usage low, since no extra copies of the data are made. We first display the full bytes object to show the complete binary data. Then we take a slice of the first 10 bytes as the header and print it, demonstrating that slicing produces a new bytes object containing only that portion. Next, we slice and print the remaining bytes as the payload, separating it from the header. This illustrates how slicing can divide a bytes object into meaningful parts, and that each slice is a new copy, even if its content looks the same as part of the original. This example shows that slices of a memory view can be converted back into regular bytes. We take a slice representing the header and use the method that turns the view into a bytes object, proving that the view can be materialized as independent byte data. We then do the same for the payload slice. This demonstrates that while a memory view lets you slice data efficiently without copying, you can still obtain a full bytes representation whenever you need it. We first check whether the memory view created from the original bytes is read-only, since memory views can share the same underlying data without copying it. Knowing if it is read-only tells us how we are allowed to modify or access that data. We then check the read-only status of the header slice of the memory view, which should also be read-only because the original bytes are immutable. Finally, we confirm that the payload slice is read-only as well, showing that all slices derived from the original memory view inherit the same access restrictions as the original bytes. This script shows how to use a memory view with a bytes object in Python to avoid copying data and save memory. It begins with an immutable bytes object, then creates a memory view that shares the same underlying buffer, so no extra memory is allocated. Both the original bytes and the memory view are sliced into header and payload parts, and these slices contain identical data when printed. The important point is that memory view slices are views rather than copies, which is more efficient, and they remain read-only because the original bytes object is immutable. This demonstrates how memory views help handle large binary data efficiently without unnecessary duplication. Zero-copy slicing. Memory view objects enable zero-copy slicing of binary data, meaning you can work with parts of the data without creating new copies in memory. In contrast, slicing a regular bytes object produces a separate copy, which can be inefficient for large datasets. A memory view instead acts like a window onto the original data, so slicing it just creates another view of the same underlying bytes. This approach reduces memory usage and can improve performance when processing large binary data. Zero-copy slicing with memory view improves performance by letting slices share the same underlying data instead of creating new copies. This is especially helpful in data-heavy tasks like processing sensor streams, real-time analytics, or multimedia, where you can keep one memory view and create many small, lightweight slices from it. These slices still reference the original data, which reduces memory usage and speeds up processing, while allowing you to work with each record independently. When using zero-copy slicing, you must carefully manage object lifetimes and data ownership because all slices reference the same underlying buffer. That buffer has to remain valid and unchanged while any slice is still in use, or the slices become invalid. If the buffer is mutable, a change made through one slice will appear in all overlapping slices, which can be either helpful or dangerous. To use memory views safely and efficiently, define clear rules in your code for how the buffer is managed and whether slices are treated as read-only or mutable. Python code, zero-copy slicing. This section explains how memory views allow zero-copy slicing, meaning slices share the same underlying buffer instead of creating new byte storage. When you create slices from a memory view, they all reference the same data in memory. As a result, if you modify the data through one slice, those changes are immediately visible in any overlapping slices. This demonstrates how memory views provide efficient, shared access to the same bytes without duplicating them. We begin by creating a mutable byte array, which is a changeable sequence of bytes. It is initialized with a series of integers that represent simple sensor readings in inches, starting at 10 and increasing by 10 up to 80. This gives us a simulated buffer of sensor data that we can modify. By changing the contents of this byte array, we can observe how those changes appear in different views that share the same underlying data. A memory view created over a byte array lets us work with the underlying buffer directly without making copies of the data. It acts like a window into the existing bytes, so we can access and modify them in place. This approach is especially useful for large datasets because it supports efficient slicing and shared access to the same memory. As a result, operations can be faster and use less memory compared to copying data. We create two overlapping slices from the memory view of a buffer to show how they share data. The front slice takes the first 4 elements from positions 0 through 3. The back slice starts at position 2 and also takes 4 elements, ending at position 5. Because these slices overlap, they contain some of the same elements from the original buffer. This shared underlying data means that changing values in one slice can also change what we see in the other. The code first prints the current state of the buffer and the 2 slices before making any changes. It converts them into lists so their contents are easy to read. This establishes a clear picture of the initial data. With this baseline, we can later see how modifying one slice affects the others because they share the same underlying memory. In this example, we modify an element inside a slice taken from the end of a memory view, changing its second element to 99. Because a memory view is just a window onto the original byte array and does not make a copy, this update directly changes the underlying data. As a result, the modification is immediately visible in the original buffer. It also appears in any other slices that overlap this region, illustrating that they all share the same storage. After changing the data through the back slice, we print the original buffer and both slices to compare them. The updated values appear in all 3, showing that a modification in one view affects the others. This confirms that the slices and the original buffer share the same underlying memory. The example illustrates zero-copy behavior, where multiple views reference the same data instead of creating separate copies. The code prints the unique identifiers of the buffer, the memory view, and its slices to show that, although they are different objects, they all refer to the same underlying bytes in memory. This illustrates a key feature of memory views. They allow multiple views of the same data without copying it. As a result, you can manipulate data efficiently, since changes through any of these views affect the same shared storage. This script shows how memory views in Python enable zero-copy slicing of data. It creates a mutable byte array to represent sensor data, then builds a memory view over it so slices can be taken without duplicating the underlying bytes. 2 overlapping slices are created and printed along with the original buffer to show they share the same data. When one slice is modified, the change appears in the original buffer and the other slice, demonstrating that they all reference the same memory. The script also confirms that, although the buffer and slices are different objects, they share the same memory space, highlighting the efficiency of memory views for large data handling. Editing byte arrays safely. A memory view of a byte array gives you direct access to the original data instead of creating a copy, so any change made through the memory view immediately updates the byte array, and changes to the byte array are instantly visible through the memory view. This makes it efficient for working with large binary data because it avoids extra memory allocation. However, it also means you must edit very carefully, since incorrect modifications can corrupt data that other parts of your program rely on. In practice, treat the memory view as a shared way to edit the same underlying data, and plan your changes precisely. When working with a memory view on a byte array, you must carefully match the size and layout of the data you write to the exact region you are modifying. Any values you store should have the correct length and format, such as a specific timestamp or status code. Writing too many or too few bytes can cause errors or shift later fields, creating hard-to-find bugs. In situations like updating a file header or changing an image buffer, always check lengths and ranges before writing, and clearly document which byte positions hold which fields. When using memory views to edit byte arrays, you must manage shared access and the lifetime of the underlying data carefully, because multiple memory views can overlap. A change made for one purpose can unintentionally affect other parts of your program, and in streaming scenarios, this can even lead to race conditions between readers and writers. To reduce these risks, define clear ownership rules, such as treating certain slices as read-only, and coordinate when and how different components update the data. Also, do not resize or discard the original byte array while any memory views are still active, since this can invalidate those views and destabilize your application. Python code. Editing byte arrays safely. This section explains how to safely edit a byte array through a memory view without creating unnecessary copies. When you change data through the memory view, the original byte array is updated immediately because they share the same underlying buffer. To use this correctly, you must be careful about the size of the edits, the positions you modify, and how long both the memory view and the original byte array remain in use. The goal is to show that efficient, in-place updates are possible while still keeping buffer sharing and lifetime management safe. We begin by creating a byte array called packet that holds a simple data packet made up of a header, a temperature value, and an end marker. We then display the original contents of this packet so we have a clear reference before making any changes. This initial printout helps us see exactly how the data looks at the start and makes it easier to track any modifications we apply to the byte array later. We first create a memory view that selects the first 4 bytes of the packet, which make up the header. This lets us work with the header directly without copying any data, saving memory and improving efficiency. Then we create another memory view that covers bytes 4 through 11, which hold the temperature data. By using memory views for both the header and the temperature section, any changes we make are applied straight to the original byte array. We begin by showing the current state of the header by converting its memory view into raw bytes, which reveals the original header content before any changes. We then do the same for the temperature field, converting its memory view to bytes to see its initial value. These initial views serve as a baseline so we can clearly compare and verify the modifications we make later. To update the header bytes safely, you first create new header data that is exactly the same length as the existing header view. This length match is required because the memory view can only be replaced with data of the same size. After confirming the lengths are equal, you assign the new header to the memory view slice. This directly overwrites the underlying byte array, so the header is updated immediately in memory. We first prepare a new set of temperature bytes with the required length of 7 bytes, matching the temperature section of the packet. We then verify that this new data is the same length as the existing temperature view, so the replacement will fit correctly. After this check passes, we overwrite the temperature bytes directly in the memory view. This updates the original byte array in place, applying the changes immediately without creating extra copies. We verify the header changes by converting its memory view back into bytes and printing the result, which shows the updated header content and confirms the modification worked. We then repeat this process for the temperature field, converting its memory view to bytes and printing it to confirm that update as well. By checking both sections in this way, we ensure that edits made through the memory view correctly change the original byte array as intended. We finish by printing the entire packet to verify how the edits were applied. This output shows that any changes made through the memory views appear directly in the original byte array. It confirms that the modifications were carried out safely and correctly, and that the memory views and the underlying data stay perfectly in sync. This script shows how to safely modify a byte array using memory views so that changes appear immediately in both the view and the original data. It starts with a packet that has a header and a temperature field, then creates separate memory views for each part. After preparing new byte sequences of matching length, it overwrites the header with a new value and updates the temperature field through these views. Finally, it prints the modified packet to confirm that the updates were applied correctly and efficiently, without making unnecessary copies of the data. In this lecture, you learned to use Super to call parent class implementations correctly in single and multiple inheritance scenarios. Define and use class method and static method to represent behaviors tied to classes rather than instances. And create and use memory view objects to share slices of binary data without copying. In the next module, Module 8, we will go over errors and exceptions. Thank you for your attention. See you all in the next lecture.